Today we're going to talk about a technique of integration called partial fractions. And what I'm going to do is I'm going to go backwards. So you see where things are coming from, and then I'm going to show you how to obtain things. So let's say that you have um, something of the form like 1 over x plus 2 or whatever number you want, x minus 3, and then minus 3x plus 4. And let's say that you would want to combine these or add them. You would do a common denominator. So your common denominator would be x times x minus 3, just the product of all of them, x plus 4. And then, well, I'm not going to be able to fit all of it here, am I? Well, we'll see. And so what I would get here, the 1 would have to be multiplied times these two guys, because that's missing to obtain the whole denominator. So I would get x minus 3 times x plus 4 for the first term. Alright, so for the second, what I would get would be 2 times this and this, because that's what I'm missing to get that other term. So this is the only one I have. The other ones I have to multiply times that. Okay. So I'm gonna have plus 2 times, whoops, change colors. So plus 2 times, and then the remainder, so x times x plus 4. Let me write x plus 4 times x. And the last one, minus 3 times, and I'm gonna have to have the other two terms. Well, I didn't really have any room. So I'm gonna go ahead and FOIL all this out and then collect like terms. So like on the internet where they say a few minutes later. So I'm gonna pause and do it. Alright, so after you FOIL everything out and collect like terms, you notice that, or you obtain this expression right here. So now you say, so why in the world did he do this when we're trying to talk about integration or a technique of integration? So what I'm going to do is I'm going to eliminate all this, and I'm going to show you how we use this idea to integrate. Okay, so keeping this in mind, this identity here, imagine that I give you this question in the exam or in homework. I say integrate this. And you start looking, well, maybe if I do a u substitution and I do the denominator, well, if you do u equals x cubed plus x squared minus 12, you would have that the du is going to be 3x squared plus 2x. You don't have that up here. So you realize that, well, there maybe I can factor, and there's a common factor here, and I can cancel things. Nothing is really gonna work. Trigonometric integration, well, it's not going to work. By the way, when I fold everything out, my goodness, there. So even worse, your denominator had even more things. So then, if you would know, then on the other hand, that this equals this, then you can integrate, because you can just say, well, if you get the integral of 1 over x, you can do that. If you do the 2 over x minus 3, I use substitution, u equals x minus 3, du equals dx, no problem. And then here, x plus 4 dx. You can integrate all these two with a u substitution. The first one just natural log of x, absolute value of x, sorry. 2 times the natural log of x minus 3. Remember, you need to do a u substitution, because if for whatever reason, let's just imagine for 1 second that I had a 2 here, then my du is not dx, it's 2 times dx, and I have to pay with a dividing by a 2. So I'm not doing the u substitution right now because these are straight up du equals dx. But if you don't have a linear term here, or the linear term, sorry, doesn't have coefficient 1, then you may want to be careful and do use substitution. But at the moment, I'll just go ahead and write it. And trust me, that's a very common mistake in this type of problems, where people uh, do the whole algebra, the whole partial fraction. This, by the way, this decomposition from here to here is called a partial fraction decomposition, and everybody does the partial fraction decomposition well. And then when they integrate, if you had a 2x or 3x, they forget their use substitution and they ruin it. So the moral of this little introduction um, is that if you have an expression, firstly it has to be a proper rational expression. If this is not a proper rational function, meaning that the degree of the numerator is larger than the denominator, the first thing you have to do is a long division. So you're gonna make it into a proper um, rational function first. But let's just focus on proper rational functions that we cannot use substitution, we cannot use trigonometric substitution, and see how we can address them. And the way we're going to address them, if we can factor them nicely, is going to be partial fractions. All right, so let's go ahead and look at an example, and I want to show you how you start finding your partial fractions. And then I'm going to do, there's several techniques you can use, there's several ways of doing it. At least I can think of 3. So every example I'm going to do it a different way, or a different technique, if you will. And you pick the one, whichever, or the one that works best for you. All right, so let's go ahead and write a problem. All right, so let's take a look at this one. So your goal would be to convert, so we're gonna compute it here like a little aside, which is gonna be more of a whole row below, and we're gonna use this space to compute our integral. All right, so what our goal is to write 7 minus x over x squared minus 2x minus 3 is to write it as a over, oh, by the way, I should have firstly factored, I suppose. So if the first thing you want to do is factor your denominator to see what kind of expression you're dealing with. So I want to do probably negative 3 plus 1. Then that's going to give me negative 2 with new item, negative 3 when you multiply, so that looks good. So I'm going to write it as a sum of proper rational functions. So if I want to break these two denominators up into two fractions, each one with a denominator, well, these are degree 1. I need to have proper rational functions, so the degree has to be 1 minus 1, so it has to be 0 degree. So you're always going to be going a degree less, 1 less, to make it a proper rational function. So that's the first thing you want to do. You don't want to be adding things that are not proper. So at the moment we just have linear polynomials or linear expressions in the denominator. Due to the fundamental theorem of algebra, you can have only linear and or quadratic terms in the denominator, because anything else should be factorable. Of course, is it easy to factor? Well, that's a different question, but should be factorable. There will be some quadratic polynomials that will be irreducible, but other than that, you should be able to break it up into linear and quadratic. Anyway, so I'll give you things that you are going to be able to factor anyway. So here we go. All right, so you're going to look at this expression, and you're going to do your, so how did we go from the nice expression to the quote-unquote ugly expression? We did a common denominator, right? So I'm writing my nice expression. To go back to the quote-unquote ugly expression, I'm going to be doing a common denominator. So if you don't like common denominator, this section is going to be a little bit annoying, but you'll get used to it. So and there's one of the methods that doesn't quite use the common denominator, so called Heaviside method, so maybe you prefer that one. But in any case, I'm going to grab this guy and multiply it times this guy. I'm going to do my cross multiplication, and then I'm going to grab this guy and multiply it times this. So what do I get? Well, I get a times x plus 1, and then plus b times x minus 3. So from that expression here, I notice that the denominators are the same, so the numerators for the expression to be the same better be the same. So I get a times x plus 1 plus b times x minus 3. So what I can do to solve for a and b, because that's what I'm looking for. Why? Because if I have a and b, I can write this out equals to the integral of whatever a is over x minus 3 plus b over x plus 1, and I can integrate. So to solve, what I'm going to do is think about what happens when x is negative 1. If you evaluate at x equals to negative 1, we will have that this term here is going to cancel, because negative 1 plus 1 is 0 times a, whatever, that's 0. So I can evaluate this at negative 1, and I'm going to obtain minus negative 1 is going to be 8. And here I'm going to have this term disappears, as we said, and I'm going to have that b times negative 1 minus 3 is going to give me an equation. This is going to be 8 equals negative 4b. So you're going to have 8. I was going to just solve, but no. Negative 4b would be nice to actually show that step. And dividing by negative 4 on both sides, I get that b is negative 2. Somehow it went from upper to lowercase. There you go. Change it again. I think we can do it here. It shouldn't take that much room. The other number I want to evaluate at is at x equals to 3, because at 3 this will cancel. So at x equals to 3, and I can solve for a at that point. So at x equals to 3, I want to have that 7 minus 3 is equal to a times 3 plus 1. This is going to be 4 equals 4a, and that gives me a equals 1 when I divide both sides by 4. Alright, so with that, I have that a is 1, b is negative 2. You gotta remember that? I hope I will remember that. So this is going to be the integral of 1 over minus 2. I do remember what a and b are, but I don't remember who goes with who. A is going with x minus 3, and b is going with x plus 1. dx. And now you can integrate. Again, remember you're going to be doing a u substitution. U equals x minus 3, and then you get the integral of 1 over u du, which is just going to give you, it's just going to give you the natural log of the absolute value of x minus 3. And here you're going to do a u substitution. U equals x plus 1. Your du is going to be dx. So you're going to end up having the integral of negative 2 over u du. That's going to be negative 2 natural log of absolute value of u. Oh, well, let's not write u. Let's write x plus 1. We already know what. Take back our substitution. Because as I've said before, nobody cares about you. They care about your x's. I learned that from my office mate. Anyways, that's going to be our answer right there. Alright, so let's go ahead and this method is, I don't really know if it has a name. Let's do another one, and I want to do the one that is called Heaviside. The other one, I don't really know what name it has, but as I said, some people prefer one method, other people prefer the other, and other people prefer yet the other one. So that's why I presented 3 of them, and you choose which one you like. Now, I'm going to only be addressing linear, non-repeated factors in the denominator in this video. Then in the next video, I'm going to address quadratic, and I'm going to also address repeated factors, so we can talk about them. Alright, so let's go ahead and write another one of these. Alright, so now we have this one where I'm going to do the Heaviside method. And so my first step is going to be to factor the denominator. In this case, I know there's a common factor x because this term ends with an x. And then you see there's a quadratic. That's going to be the case often. Well, why did I put the square? I'm factoring an x out, plus 2, and then 2x plus 1 dx. And then I'm going to factor one more time, and then 2x plus 1 all over x minus 2 minus 1, I suppose, dx. Alright, so now I'm going to try to write this expression. So I'm going to go down below. I'm going to leave myself enough room to finish the integral once I have the partial fractions computed. So my goal is going to be writing the 2x plus 1 over x times x minus 2. By the way, the method I'm about to do only works when you have non-repeated terms. When you have repeated terms or squares, you gotta be a little bit, or actually you have to be careful. I would only do it with linear terms, and when you have repeated terms, what's happening is it's gonna just, the method is just gonna give you one of the coefficients that you need for the term that appears repeated. So if you have squares, so say if this one would be a square, that's what I mean by repeated. You want to be careful with this method. It works. It gives you one of the two coefficients. But anyways, we are not at that point. But I just want to warn you of what I'm gonna do right now, and when it's useful to do it and when it's not. And to motivate the idea here, I'm going to go back to our previous example, and then I'm going to apply it here. So if we pay a lot of attention to what happened here, if you look at, I need this. So whenever I evaluated at x equals to -1, I got this part evaluated at -1. So this right here, this is what happened here, okay? And then what I'm dividing by, whenever I divide on both sides, I divide it by this -4. But that -4 is this evaluated at -1. So to obtain b that has this x plus 1 involved, I'm evaluating the fraction on left hand side at every point but x plus 1. Why? Well, because if I would have done it a little bit more carefully, I would have noticed something. Instead of multiplying or doing common denominator at everything, let's copy this, my partial fractions that I'm trying to obtain. If I would have multiplied both sides that x plus 1, cancel this x plus 1, and you get a times x plus 1 over x minus 3, and then plus the x plus 1 cancels, plus b. When you evaluate this at x plus 1, this whole term goes away, and then you just get that b is this expression ignoring the x plus 1 evaluated at x equals to -1. Okay, so let's try to put that in action in our problem where we have more terms. So what I would want to do to obtain b, so I'm going to try to be a little bit detailed so you see how it works. So for well, you can do b, but alphabetical order mandates that I do a, I suppose. So for a, I'm going to evaluate this expression. So what am I dividing here a by? I'm dividing it by x. So the one term I should not have is the x, because that gives me the 0 in the denominator. So I'm going to evaluate the expression 2x plus 1. So I should write a equals that. I'm going to ignore that x, and I'm going to copy everything else from my expression on the left hand side. And I'm going to evaluate this at x equals to 0. X equals to 0 is the number that makes this equal to 0. So I evaluate it at 0, and I get 1 over, and then here's 0 minus 2, negative 2, 0 minus 1, negative 1, I get 1/2. So you see, it's a lot easier. Now for b, I'm going to look at what is dividing b. Is this x minus 2, and I'm going to copy the whole expression without that x minus 2. That's equivalent as multiplying everything times x minus 2 and then evaluating at x equals to 2. So I'm going to write that expression that I have on left hand side, ignoring my x equals to 2 term, or x minus 2 term rather. So x times x minus 1, and I evaluated at that x equals to 2, the one that gives the 0 on that one that I ignored. So evaluating at x equals to 2, I get 2 times 2, which is 4 plus 1, 5, over 2 times 2 minus 1, which is going to be equal to I'm not getting the right number that I had gotten. Oh well, I unfortunately, probably, I think this was a 5 minus 1, because in what I computed was a 3/2. So now we're gonna get different numbers, so woohoo. Unless I messed up anywhere here in my calculation. Let's see, my factoring, is that correctly? X plus 2, and then I did a minus 1 minus 2. Yeah, everything looked good. Okay, well, I must have messed up a coefficient. I'm well known to do that. It doesn't matter. We're just gonna get fractions that are slightly different, and you can always check your work. I'm gonna show you how to do it. That's actually a good idea. The video's already kind of long, so I may just do two techniques. Alright, so for c, I'm going to look at what c is divided by, x minus 1, and I'm going to ignore that x minus 1, and I'm going to evaluate everything at x equals to 1. That's what makes that x minus 1 equal to 0. So write 2x plus 1 over x times x minus 2. I'm still baffled by the previous one. I'm still looking at it. At x equals to 1. That's the one that makes this 0. That's the one term I ignored. So I get 2 times 1 plus 1 is 3. And then this is 1 times, I'm going to have 1 minus 2. So I get, this is going to be 3 over negative 1. So negative 3. Minus yes, okay, definitely my coefficients are not the same ones I had computed, so I messed up somewhere when I copied the problem. It's okay. We'll confirm. So to confirm, what would you do? Well, to confirm, you can put your coefficients a, b, c, you do a common denominator, and you should obtain this back here. Alright, I'm gonna do that real quick. I'm gonna pause the recording and make sure it's true. I caught myself up. Alright, so we multiply it out and make sure that it works out. Negative 3/2 minus 5/2 is negative 8/2, which is negative 4 plus 6 equals 2. 2x plus 1. Good, we did it right. So these are our coefficients. Of course, if your calculator has the capabilities, you may want to do this calculation in the calculator to verify. Alright, so once you have that, we can plug it back in. So we get 1/2, or the integral of 1/2, or 1 over 2x, if you will. Although, no, let me not do it that way. I want to write it as 1/2 over x, because then you don't think about a u substitution, u equals 2x. You just grab that 1/2, move it out, and then just do your integral of 1 over x. So I like writing it like this better. And then plus b, which is 5/2, so plus 5/2 of x minus 2. Again, you can do u equals x minus 2 for your integral. And the last one was what? Minus 3. So minus 3 over x minus 1. All of it dx. And so your integral then becomes 1/2 of the natural log of x, absolute value of x, plus 5/2 of the natural log of x minus 2. And I forgot to say one thing. Let me finish here writing natural log of x minus 1 plus c. In the book, they will put this 1/2 as a square root. This is going to be square root of the x minus 2 to the 5th. And then there's going to be cubed. Then they're going to collect it, and they're going to end up with something like the natural log of square root of x times the square root of x minus 2 to the 5th. Goodness, what did I do? Because I never, this, please don't do that. Or they just do square root of x times x minus 2 to the 5th over x minus 1 cubed. I don't care about this. If you're in my class, don't even worry about it. This is perfectly fine by me. Now, if you're not in my class, I never said anything. Your professor is right. You should do it this way. That you do. Anyways, so that I'm gonna stop it right here because this video has become a little bit long. So I showed you two methods. The other method I'm gonna show you whenever I do uh, repeated terms or quadratic terms. So thank you for watching this. This is the first video on partial fractions. There to be at least one more, maybe two more. So let me know if you have any questions. And if thank you for watching, and until next time, see you in the next video.